Hello dear students, welcome you all for transmission and distribution class. So continue with the underground cables, that is at module 4. So today we will see the current carrying capacity of underground cables. Okay, the safe current carrying capacity of an underground cable is determined by the maximum permissible temperature rise. So obviously we know it that permissible current carrying capacity is dependent upon the purely its thermal capacity, or how much heat it can withstand. Okay, the cause of temperature rise is the losses that occur in a cable which appear as a heat. The losses are that different losses are occur in the cable. The first type of loss is the copper loss in the conductors. Second one is hysteresis losses in the dielectric, and the third one is the eddy current losses in the sheath. The safe working conductor's temperature is 65 degrees centigrade for armored cable and 50 degrees centigrade for the lead sheathed cable laid in ducts. Okay. The maximum steady temperature conditions prevail when the heat generated in the cable is equal to the heat dissipated. The heat dissipation of the conductor losses by its conduction through the insulation to the sheath from the which the total losses, including the dielectric as well as the sheath losses, may be conducted to the earth. Therefore, in order to find the permissible current loading, the thermal resistivities of the insulation and the protecting covering and the soil must be known. Okay, now we will see the what is exactly thermal resistance. The thermal resistance between 2 points in a medium is equal to the temperature difference between the 2 points divided by the heat flowing between them in a unit time. So as we potential differences and all we are seeing between 2 points, like that the thermal resistance we are finding with the 2 points only. Here thermal resistance S is given by temperature difference between the 2 points divided by heat flowing in a unit time, in a given time unit. It may be 1 second, 1 hour, whatever unit we are using there. Okay, fine. In SI units, heat flowing in a unit time is measured in watts only. So thermal resistance S is equal to temperature rise divided by watts dissipated. That is what here thermal resistance S can be given by temperature rise T divided by the watts dissipated P. Clearly, SI units is a thermal resistance is given in the centigrade per watt, so it is called as thermal ohm. You can see thermal resistance is given by temperature rise, that is the temperature rise T is given in either centigrade or in Fahrenheit or in kelvins, whatever it may be. So for the time being we will consider it as a centigrade. So percentage degree centigrade per watt. So the thermal resistance we can give a unit for this is centigrade per watt. Okay, so like electrical resistance, thermal resistance is directly proportional to the length of the direction and the transmission of heat, and inversely proportional to the cross section of the area at the right angles to the direction. So the thermal resistance is proportional to L by A, where L is length, A is the area, or proportionality constant K is used here. S is equal to K into L by A, where K is the constant of proportionality and known as the thermal resistivity. Like in your electrical resistance we are seeing the rho as the resistivity. Here same thing, K is the thermal resistivity, where K is given by SA by L, or it is thermal ohm into meter square by M, or it is unit of the K is thermal ohm meter. Now we will see the thermal resistance of dielectric in a single core cable. So let us find the thermal resistance of the dielectric in a single core cable. Considering a figure there in 11.21, R is the radius of the core in the meter, R1 is the inside radius of the sheath in meter, and K is the thermal resistivity of the insulation. You can see there everything is clear. R is the core, R1 is the sheath radius. Okay, now consider a length 1 meter length of a cable, and the thermal resistance of a small element, and that is thickness of dx at the radius of x. You can see there a small element dx is chosen, the thickness which is at the x radius away from the center. Okay, so the thermal resistance of that particular small element is given by ds is equal to K into dx by 2 phi x. We know ds is nothing but K is the proportionality constant, that is the thermal resistivity, into length. Length is how much? dx, and area is 2 phi x. Now the thermal resistance of dielectric is given by total this ds is integrated we will get integration from R to R1, because from the outer, from the conductor to the inner of the last thermal or inner sheath. Okay, so that is R to R1. We are integrating it one, we will get the values as k by 2 phi into integration R to R1 1 more x into dx, or S is equal to k by 2 phi natural logarithm of R1 by R thermal ohms per unit length of the cable. The thermal resistance of lead sheath is small and generally neglected in the calculations. So permissible current loading, we will go with the permissible current loading here. So when considering the heat dissipation in underground cables, the various thermal resistance providing a heat dissipation path are in series. Therefore, they add up like electrical resistances in series. So consider a cable laid in the soil. Let I is the permissible current per conductor, N is the number of conductors, R is the electrical resistance per meter length of the conductor at the working temperature, S is the total thermal resistance per length, and the T is the temperature difference between the conductor and the soil, neglecting the dielectric and heat losses. So we have a power dissipated is equal to N into I square R, where number of conductors into current square into resistance, or power dissipated we are knowing is temperature raised by thermal resistance, or these two can be equated by Ni square is equal to T by S, or permissible current I is given by square root of T by NRS. So it should be noted that when cables are laid in proximity to each other, the permissible current is reduced further on account of mutual heating. Let us see one problem here. This problem gives us a single core cable is laid in the ground. The core diameter is being 30 mm and the dielectric thickness is 40 mm. The thermal resistivity of the dielectric is 5 thermal ohm meters, and the thermal resistance between the sheath and the ground surface is 0.45 thermal ohm per meter length. Neglecting the dielectric and sheath losses, estimate the maximum permissible current loading if the temperature difference between the conductor and the ground surface is not exceed 55 degrees centigrade. The electrical resistance of the cable is 110 micro ohms per meter length. Okay, these are the things given here. We will go for solving the problem. The thermal resistance of the dielectric of cable S1 is given by k by 2 phi natural logarithm of R1 by R. This we are knowing. So here k is 5 given in the problem, and R is 30 by 2 because diameter is 30 given, so it is 30 by 2 15 mm, and R1 is thickness is given 40, so we can add 15 plus 40, that is 55 mm. So by putting all the values, we will get the S1 value as 1.03 thermal ohms per meter length. Thermal resistance of the soil S2 is given by 0.45 thermal ohm per meter. This is given. So if you add the total thermal resistance, that is S is equal to S1 plus S2, we will get 1.48 thermal ohms per unit meter length. Now once we find out the S, we need to calculate the I. We are knowing the equation of I is equal to square root of T by NRS. T is 55 degrees centigrade, they are given to be limited to 55 degree. N is only one here, no combined conductors are there, only one single core. Then R value is given, that is 110 micro ohm. S is 1.48, we are just now calculated. By putting all these things in the equations, we will get a value of current that is the permissible current is 581 amps. So we can conclude that permissible current loading is 581 amps can be used for the this cable. So this is regarding our thermal resistance of the cable. So current carrying capacity of the underground cable, starting from the different losses which is happens in the cable, and what is the thermal resistance, and finding the thermal resistance in a cable. Then finally we concluded the permissible current loading and calculated the on problem on these things. So once again you go through these things and you will get the idea regarding the current permissible loading, maximum current loading, permissible current loading. So if you find any difficulties, you can ask me. Thank you.